section. In this video we're going to look at the sine rule, which you would have seen at GCSE. So last time we looked at the cosine rule. So if we had, say, a sort of generic triangle, right, with points A, B and C, and that's side A, length A, this is length B and that's length C. Then the cosine rule talked about when we are dealing with three sides, all three sides of the triangle on one angle. So it was a squared is b squared plus c squared minus 2bc cosine of a. But obviously the angle at A is here. And so that's the cosine rule with three sides and an angle. Now what we're going to look at then is the sine rule. Now, the sine rule is this. It is a over sine of A equals b over sine of B. Meaning, one length and the opposite angle. So the angle A here is facing the side little a. So the side over its opposite angle, A over sine A, is the same as another side versus its opposite angle. So the length B here, and so that would be angle B. And so sort of the ratio between two lengths and their angles are equal, essentially. So again, to reiterate, the length A, any given length, and its opposite angle, here, then that fraction is equal to another fraction of another side and its opposite angle. So say b over sine of b. You can also then say the other side as well, c over sine of c. If we then said that was angle c at c, where obviously it's facing that side there. And that is the sine rule, essentially. Again, it should be a recap from GCSE. Obviously, we'll go through some examples, which puts that in action. Because it might look a bit weird at the moment, just stating the formula. But we're going to be looking at another concept that isn't in GCSE, so do stick around. Something called the ambiguous case, which you would not have seen at GCSE. But we'll go on to that later on. But for now, let's have a look at applying this formula. And again, you don't need to know the proof for it. I've checked the spec. You need to know how to use the formula, right? But you don't need to prove it. Again, if you want to see a proof, there's probably multiple videos on YouTube. The textbook goes through it. And again, the idea is essentially, if you have the same triangle, then you consider the vertical height, right? And then that splits it into two right angle triangles, and then you use SOHCAHTOA basically. If we call the side like C, A and B, right? Then you use SOHCAHTOA, and eventually you can deduce this sort of that formula, right? But anyway, I'm not going to go over that here, just save on time. But yeah, let's have a look at using this formula then. Let's have a look at some examples. Right. Example 5. In triangle ABC, AB is 8 centimeters, angle BAC is 30, and angle BCA is 40. Find BC. So again, I find it a good idea to sort of draw a triangle, right, to represent this, to see what I'm doing. So if you have a point A here, say, then point B, say, would be there. That would be 8 centimeters. Then C will maybe be there, and then we draw it that way. Okay, and then we also know stuff about angles as well. So angle BAC, so it's the angle at A here, that's 30, and the angle BCA, that's the angle at C, because again, how we do this sort of angle notation, BCA, the C is in the middle, so the angle is at the C. The point C there, so there we are, and that is 40. Okay, so that's our triangle. We need to find the length BC, so that would be this length here, which I'll call X. Okay, cool. So this is going to be sine rule, because sine rule is two angles and two sides we're dealing with. The cosine rule was 3 sides and an angle, but what we have here is 2 sides we're dealing with and 2 angles. So we'll be considering the sine rule here. Anyway, so the sine rule is A over sine A is again B over sine B. So we've got a length over its angle over another length and its angle. So first of all, x is the side, right? So we're going to do x over the angle opposite the side. So the angle facing the side is 30, so the opposite angle is sine 30. So the 30 here is again opposite or facing that length, right? BC, that side x. Okay, so then that's going to equal another side over and the angle. So we know this angle 40 is facing the 8, so it's opposite the 8. So it's going to be 8, which is the length, over sine 40, the angle. Okay. So there we are then. So this is actually an equation for x, and we can solve. So we can just put all these numbers in the calculator, because then we're going to get, well, x over sine 30 firstly. Well, sine 30 is going to be a half. And then that's going to equal 8 over sine 40, which if I do all that in the calculator, 8 over sine 40 is 12.4457 ... And so then, x then, if I then times both sides by a half, I get that x is 12.4457 times a half is 6.222 ... which I'd say 6.2 centimetres to a decimal place, right? And there's my answer. Okay, cool. There we are. Right, okay, so there we are. Alternatively, this does look a weird fraction. I'll break it down a little bit, what I've done here to solve this bit, because it looks a bit weird, right? X over a half. This you can simplify this by basically recognizing it. This is x divided by half, right? But then you do KFC, keep flip change. That's then the same as x times, and then you flip that fraction to be 2 over 1, which is just 2. So then that's the same as 2x. So this is basically saying 2x then is equal to 12.4457. Hence x then I'll divide by 2, or times by half. Okay, so that's how I got that answer there. I thought I'd break that down, because it does look a bit weird. And in general, if you do have weird fractions, do it like that if it helps. Okay. Okay, so we're on this example then. I should say, I did check this, and this is a bit of an error from the textbook, right? It's not meant to say angle ABC, it's meant to check angle BAC is equal to 35. Right, okay. Okay, so with that correction in mind, it says in triangle ABC, angle AB is 3.8 centimetres, BC is 5.2, and angle BAC is 35. Find angle ABC. Okay, so again, let's draw a rough sort of idea of a triangle, right? To just put this information in, so we can we can put the lengths and the angles in. So anyway, angle, so point A is here, point B say there, and point C say there. I'm not worried about how accurate the triangle is per se, I'm just drawing a rough idea, a rough sketch of one. So angle AB is 3.8, let's put it here. BC is 5.2, and we don't know AC, that's okay. But we also know angle BAC is 35. Now the angle in the middle is A, so it's going to be at A. So the angle here is 35. We need to find angle ABC. So that's going to be here, which I'll call theta. So actually this time we need to find an angle, not a side. But that's not a problem. Okay, so again, we've got two sides and well, two angles we're dealing with as well. So I'm thinking the sine rule, right? So I'm thinking A over sine A is B over sine B, which is the sine rule again. So I'm going to apply that somewhere. And this is where the idea of opposite angles is crucial, because the angle facing 35 here is 5.2. Cool. But the angle facing 3.8, the other side we know, well, that's actually this angle here. That's angle C. I'll call that angle C. Not this angle theta that we want. Okay. The side facing theta is this side here. So we do not say that 3.8 over sine theta is 5.2 over sine 35. We do not say that because this fraction is not true. Because sine theta, the angle theta, is not facing the angle 3.8. It's opposite to this side here, AC. We do not know what AC is, so we can't use it for theta. But what we can do is then find this angle C, this other angle. So we can start with that then, because C is indeed facing 3.8. What we can then say is, well, 3.8 over sine C is going to then equal 5.2 over the other angle, sine 35. Now what you can do here is, actually you can flip the fractions and it's perfectly the same. So therefore we can then just say sine C over 3.8 is also sine 35 over 5.2. Make sure you flip one fraction, you do the same to the other, because it's an equation. Which leads us to an alternative formula to this. We can also say that sine A over A is also equal to sine B over B. Right? So there are two ways of expressing that sine rule, okay, depending if you want to find a missing side or a missing angle. But anyway, there we are. So let's continue with this. Well, what I can then do is actually, I can times 3.8 to both sides. So I'll just get sine C is equal to 3.8 times this fraction of sine 35 over 5.2. So then I'll just put all that in the calculator. So then I'll get sine C is equal to 0.419 ... some decimal. Therefore then C, if I inverse sine, I get 24.78 and some other decimal degrees. Right, I'd say that to 2 decimal places. It doesn't tell me to round it to anything, no. But that's the angle C. Remember, I want to find this angle theta. That's the angle ABC. So I'm not done yet. But I know two angles in a triangle already then, don't I? So then to find the other angle, well, I should know that the angles in a triangle add up to 180. Well, therefore then, I can then say that the angle 35 at A and the angle at C, which is 24.78, and the angle theta has to be adding up to 180. Well, therefore then, theta is 180, take away those two. And so simply then, theta is going to be 120.218 ... degrees, and I'd say that's 120.2 degrees to 1 decimal place. Okay, there we are then. Cool. So that also is a common strategy, strategy, but a theme sometimes with certain questions. You might not be able to find a particular angle that you want, but you can then utilise the fact that angles in a triangle add up to 180. So yeah, so don't be put off by that. But there we are. So we found that angle there, and don't forget you can flip the fraction in the sine rule to find a missing angle if it makes it easier to solve it that way. but it doesn't really matter. At the end of the day, we get this angle. Right, okay, let's have a look at this question then. Okay, in triangle ABC, AB is 4, AC is 3, and angle ABC is 44. Work out two possible values of ACB. Interesting, two values, right. Well, again, let's start with our strategy. Let's we sort of draw triangles to represent this, right? So, again, say a point A here and point B there, and a point C there. Well, it's a bit wonky. There we are. AB is 4, AC is 3. Okay, it's not the most representative then. That looks larger than AB. And angle ABC, so the angle at B is 44. Okay, it's a very wonky triangle, but apologies. Doesn't really matter, it's just a rough diagram. Work out two possible values of angle ACB. So that means the angle at C, right, which is going to be, again, theta. That's the angle we want. Now, we can use the same strategy we did before, right? So, the sine rule, then, we can use the sine rule as normal. That would then be A over sine A is equal to B over sine B. And so then, what are our sides and a length? So we're using the sine rule again because there's two sides and two angles. That's the key idea of a sine rule. So, we firstly have this angle 44 here, and it's facing the 3, so that we're going to have 3 over sine 44, and that's going to equal, then, well, we have this angle theta, and it's opposite the 4, so then it's going to be 4 over sine theta. So then we just solve for theta, right? So again, to help us, we could flip the fraction, do the reciprocal, so then we can say, well, sine theta over 4 is going to equal sine 44 over 3. And so then I can times both sides by 4, or I could cross multiply, right? But I'll times by 4, so then sine theta is 4 times sine 44 over 3. And so if I put all that in the calculator then, well, 4 times sine 44 over 3, I get sine theta is 0.926 ... So therefore then I get theta to be, if I inverse sine, 67.85 ... So I'll just leave it at 67.85 degrees. Okay, so we got this angle theta. However, there's another thing to this. Let me consider the sine graph, right? So remember from GCSE, the sine graph looks like this. Somewhere like that, right? Where obviously start from 0, then 90 degrees is at like the top of the hill, right? Which is when it's sine theta is 1. So this is the graph y sine theta. And then 180 is there when it dips back to 0. Then 270 is here when it goes to dips below to -1, and then it goes back again at 360. What I'm then going to do is I'm going to zoom in and only focus on the first half between 0 and 180. That curve, that part of the curve, right? So I'm going to redraw this again. Oh. There we are. 180, 0, and then 90 would be in the middle, at 1. Right, why am I drawing this? Well, let's go back to this point here. Sine theta is 0.926. Well, if this is 1 right at the top there, then 0.926 will be like there, right? If we draw that line then, there, that is 0.926. What we're saying then, when we are solving sine theta is 0.926 for the angle theta, what we're we're basically saying is, if we draw a line 0.926, where are the intersection points with the sine curve? Well, we can spot the first one's there, but there's also another one there, which is interesting. So that implies there's actually there's actually two solutions to this, two different angles. Well, the first angle at this point here, well, that is indeed 67.9, which is what we worked out there, right? But what about this other one? Well, there's actually indeed another solution there. Well, how are we going to work that out then? Because the calculator will only give me the first solution, right? Which is 67.9 when we inverse sine. But how do we work out the other solution, where it crosses the curve there, at this angle theta there? Well, what we notice with the graph again, if I redraw the graph again, just without all the numbers annotated onto it, say there. Well, hopefully you notice it. Obviously, the middle point is 90, but actually the curve is symmetrical, right? At that point, right, 90, where the left side of the curve is indeed the same as the right side. It's symmetrical, right? So we're going to use that. Now, if I suppose I drew a line here, say a different a value, right? Right, again, there's two intersection points there and there. If we know the first one, well, the second one, so this is 180 as well, I should say, at the end there. Well, the gap between 0 and this first intersection is the same between 180 and this gap here. Well, so then we can use that to work out that second intersection point then, if I go back up. Because what I'm saying then is the gap between 0 and 67.9, between 0 and the first solution there, it's the same between the gap between the second solution and 180. So what I can do then is, well, the gap is indeed 67.9, right? Because between 0 and 67.9 is actually 67.9, right? So that's the gap between the first solution and the end. But so then at the other end, at 180, it's the same gap, the same distance of 67.9 between the solution, the intersection point, and the end of the curve at 180, because it's symmetrical in the middle, as we just seen. So we can calculate the second solution, which again is here, because the gap again is 67.9, which is going to be the same as this gap here, right, between 0 and this angle of 67.9, right? So again, the gaps are the same, right? 67.9 here and 67.9 here. Which means then, well, to get this solution then, this other point here, I need to do 180 take away this 67.9, right, to get this other solution, this other point here, right, this other value of theta there, right? So if I do 180, then take at this end and go take away 67.9, so going back to the left by 67.9, I get to this other angle, and so therefore then the other possible value of theta is going to be 180 take away this 67.85, which would get me, if I put that in the calculator, 112.15 degrees. Okay, cool. So I've got two possible values of theta then. And so yeah, in general then, with the sine rule, it will always produce two possible angles we can have, right, as we can see here, 67.8, so if I summarise then, theta could be 67.9 or 112.2 to one decimal place, we're around it. So I've got two possible solutions then, which then, if I go back to my triangle, theta could be this 67.9, or it could be 112.2, right? So I've got two possible values of the angle ACB. And so that's the whole idea, right? The fact that this sine curve, as we can see, the sine curve will always have two different solutions, right? That which I've circled there. There will always be 2 points where it crosses over with the curve, which will produce two different angles. Okay, so that's the idea then. So then, as you can see here again, to reiterate, so these 2 points here, the gap between the other end of the curve at 0 and this first point here is the same as the gap between the second point and 180, right? So the gap there is the same as the gap there. So in general then, because to work out this other angle then, if you have the first angle, again, say up here, is 67.9, then the other angle here is going to be 180 take away that 67.9. In general then, what we call this then, when we can get two possible solutions for the angle from the sine rule, we call this the ambiguous case. Ambiguous case of the sine rule, and that gives us two possible angles. So it gives us two angles when we solve it, because again the whole idea that this sort of line, right, we cross the sine curve twice, which gives us two angles. Okay, and then so because the gaps at either end of the curve and the angles, the solutions are the same, right? Then we can say that if we have the first solution theta 1, so if we have the solution theta 1, so we have one of the angles, right? Then the other solution, or the other angle, well, is going to be theta 2, the next solution, and it's going to be 180 take away this angle here, because of the fact the gaps are the same at either end. So the gap here is just theta 1, right? From 0 to theta 1, it's theta 1. So then to go from theta 2 to 180, so then to go from 180 to theta 2 here, right, this gap here, is also going to be theta 1. So then so then we take away this angle from 180 to get the other solution. Okay, if that makes any sense? By considering, well, just look at the graph, right? Because it's symmetrical, right? So again, it's the same distance away from each other, right? The two solutions. Okay, so it's 180 take away that. Okay, right. So we've got two different angles and two. Well, what about the last example we did? The last example, we only had one solution. We had to find an angle, right? We got this angle C, and then we found only one angle, right? Why is only one solution in this case for the angle? Why not two? Well, actually, there would always be two possible angles if we solve it as we just did. So I'm gonna restate, right, that question, right? So we had this triangle, right? We found, and we got to this point for finding the angle C, right? And we got this angle C is 24.78. Now, why is there not another solution like we said in that case, right? Why are we not getting the second one? Well, there would be, and again, to work that out, if we consider the sine curve between 0 and 180. Well, 24.78, the angle that is going to be roughly like there, right? Bearing in mind 90 is in the middle, right? So 24.8 is there. So the other solution, if we go across like this, would be about there, right? So that'd be the other value of C, the other angle for C. How do we work that out? Well, again, the gap at either end and the solutions are the same, which means the other solution would be 180 take away that angle. right? And if we work that out in the calculator, I get 155.22 degrees. Okay, but let's think about the solution then. Well, we got this triangle again, right? If I put in that angle then, 155, what if I add that with 35, the other angle? If I do that, I get 190.22. But hang on, shouldn't angles in a triangle have to add up to 180? I've got above 180 here. That cannot happen. So therefore that cannot be a solution then, because it will give me angles total above 180 in the triangle. So I'm going to say then, as angles in a triangle must add up to 180. That means that C cannot be 190.22. No, sorry, 155. That was the solution we got. 155.22. So therefore then, we can only accept this solution then. So therefore C is 24.78 degrees only. Okay? And so that in that case, we could only have that one solution. But you should always be from now on, always checking for two solutions when you're using the sine rule or using sine theta. Okay? Anything to do with sine, you want to be checking for two angles. Now, but obviously once you've got the two solutions, you need to check the other solution, right, the larger one, and check if it makes sense, if it's valid. Meaning, can it be an actual angle in a triangle? If it makes the angles above 180 like here, then it can't be a solution. So we should always be checking it in this way. But yeah, okay. So from now on, we should always be considering this ambiguous case, so the checking for the second solution for an angle. Okay. So let's move on to another example. Right. Okay. Let's have a look at this example then. A surveyor wants to determine the height of a building. She measures the angle of elevation of the top of the building at 2 points 15 metres apart off the ground. Use this information to determine the height of the building. So again, the building, well, the height of it is that distance there, right? So if I call that, say, H there. So I want to find this H. And I've got two triangles in weirdly. So what can I work out first of all? What can I work out? So I've got a side in this triangle, and I've got an angle. But I also can work out this angle, can't I? Because isn't the angle 32 and that angle I've drawn, isn't that an angle on the line? So then I can say that this angle here. Oh, I didn't mean to move that. I'm gonna draw some letters in. I don't know. They've not labelled it. A, B, C. Okay. I've labelled that triangle, right? So this angle then. So this angle here. Oh, this angle I'm gonna call ABC. So it's the angle at B there. Well, again, that angle and this angle of 52, they are on a straight line, right? So they have to add up to 180. So again, remember your basic angle facts. So that means then if they add up to 180, so that means 180 take away 52 gets me that angle there, the other angle on the other side of the line. So then that would be 128. So actually I can fill this in. So 128 there. There we are. It's a bit awkward, not the best drawn diagram. Not a lot of room, but there we are. So now we've got, actually I'll redraw it. So I'm going to redraw the first triangle then with that filled in. So I know this angle's 40 and I know that angle now is 128. So, and I also know this side here is 15. Well then, I got two angles and a side. I can then work out another side, because remember, two sides and two angles I'm dealing with, I can use the sine rule. Well, what side should I work out then? Let's have a think. Well, I can work out, well, again, let's use the angles to guide us, right? Well, this angle's facing that side, and this other angle's facing that side. Well, actually, none of the angles we have are facing the 15. This angle would. But we can work out that angle, because now we know two angles in a triangle. So then the third one, they'll have to add up to 100, add up to 180, right? So that's angle. So again, if this is points A, B, and C, therefore that angle then, angle at C, so that'd be ACB, is then going to be 180. Take away the other two, so 128. Take away 40, and so that would be 180 at 112. So again, it's going back to that tip I described earlier, that you might need to find other missing angles by considering angles in a triangle or on a line, right? So your basic angle facts. So now we know that's 12. So now we can find any side, right? Any second side by the sine rule. But which one? Let's have a think. Well, actually, I notice I have an overall triangle here. Between A and C, the height. Oh. And that from the tower to A. So I'll describe that triangle again. So I have this. I have the overall triangle between A and C, and the height between the tower, where C is at the top of the tower, and we know the angle there is 40. Well, actually, this is a right angle triangle, isn't it? Let's go back. This is a right angle triangle. So actually, I can use SOHCAHTOA for that. So I only need one side, right? Because I know an angle. But that's what I can work out this side, can't I? AC. I can work out this angle, this length AC, right? Here, right? I can work out that using the sine rule, right? So that means then I have the length x over the opposite angle to x. So x is facing 128. So sine 128, and then that's going to equal. Let's go back to this triangle here. That's going to then equal 15, and then the angle facing that side 15 is 12, right? The angle 12 is facing the side AB, which is 15. So we're going to get 15 over sine of 12. Cool. So then I can solve for x, right? That length x. So x is going to be sine 128 times by 15 over sine 12, which is going to be 56.85 dot dot dot. Is it given a unit? Meters. Okay. I'm not going to round it because that's not my final answer. So now I can. Now I know this set length is 56.9. Say. So now I know x is 56.9. I can fill that in. But remember, I want to work out this length h, the height of the tower. Well, again, this is a right angle triangle, right? Remember, there's an overall bigger triangle going on, right, between A and C and the tower here. Hopefully you can see that, which I've drawn again here. So I can use SOHCAHTOA because it's a right angle triangle, right? So therefore then, if we want to find h, well, h is opposite the angle, right? And this is the hypotenuse, right, which is facing the right angle triangle. Therefore, I'm going to use sine. So remember SOHCAHTOA. So sine of the angle is going to equal the opposite, which is h, over the hypotenuse, which is 56.9. Therefore, then h is then going to be 56.9 times by sine 40, which would be 36.54 not degrees, sorry, meters. So there we are then. So that's just saying 56.5 to 1 decimal place, let's say. It doesn't say to round it to anything. No. So that's the height of the building then. Cool. So hopefully you understood what we did there. Again, it's fairly common as well that you might have two triangles, but if you can work out a common length or side between them, that can help you as well. So AC again is the common side of the smaller triangle and the overall bigger one. Okay, not the easiest question, but there we are. Then for part B, state one assumption made by the surveyor in the model. Again, fairly common, weird one marker. So again, why would that not be in the most realistic model in the real world? So again, it's we could say, well, there are probably many things you could say of why this sort of triangle is not realistic. Let me get rid of all this now so I can clearly see the triangle. Well, the thing is, probably the easiest one that is applicable is to most scenarios. It's the fact that the ground is modelled as completely flat, right? You can see that here. And so if this, so in actuality again, the sort of floor, right, the ground here would not be completely flat, which would mean the angles and stuff would be quite different, and we wouldn't get like a perfect straight lines and stuff like that. So that would probably be like the one assumption is that the ground is flat. So I'll do that up here. Assumption, or completely horizontal or completely flat, that the ground level or the ground is completely horizontal. Because obviously in reality you'd expect that the grounds everywhere, like roads or anything, or paths, are not completely flat, right? They can have little bumps and edges, like kind of like that, right? Something like that. That would be like probably a more, well, it's a bit exaggerated, but it's not going to be completely 100% flat, is what I'm saying. So that would affect the model, right? But that's one assumption. Anyway, quite weird questions. When once you've seen more of them, you start to pick up kind of what the things you can say and what they expect. But anyway, so okay, thought I'd throw that in there, throw a bit of modelling in there, just to help deal with that part of the course. Anyway, let's have a look at this question then. We are told then in each of the following cases, triangle ABC as angle ABC and AB is 10. So again, let's draw a sort of situation then. So A is here again, B is there, C is there. So AB is 10. Angle ABC, so that's the angle at B, that's 30. And that's all we're given really. Part A then says calculate the least possible value that AC, which is this length here, could be. So the least value, what that is saying then, okay, this is quite difficult. This is quite a difficult question to realise because of this one idea. At GCSE, again, hopefully it doesn't. I don't think you spent much time in it. But what you need to know is between 2 points, again, say between A and C, the minimum or the least length between them, or the minimum distance, is what we call the perpendicular line, perpendicular distance, which is a line which is going to be perpendicular. So say if you have a line here and A's there, and say you have another line there and C's there, the minimum distance between those 2 points is perpendicular to it, right? What that means then is the least length occurs when they're perpendicular. So if that would mean AC then, say here. So then that means from C to B is going to be a perpendicular. Okay, that's what that means. The angle has to be a right angle. If we want to find the minimum distance AC. Okay, it's the minimum distance when it's perpendicular to a line, so it's at a right angle to a line there. So there we are then. So when it makes at a right angle to another line, then it's the shortest distance. Okay, quite a really like niche sort of idea you need to learn. It's from GCSE, but yeah. That's probably the hardest part, honestly, is realising that. But anyway, hopefully you realise then we've got a right angle triangle. We also, again, know that this length is 10 and this angle is going to be 30. So it's basically SOHCAHTOA, essentially, right? So AC then, well, we know an angle, we know a side, we know that the 10 is the hypotenuse as it's facing the opposite the right angle. While x then is opposite the angle 30, so again we're going to use SOHCAHTOA on the sine. So the sine of the angle 30 is going to equal opposite, which is x, over the hypotenuse, which is 10. Therefore then x then is 10 times sine 30, which is going to be well, sine 30 is a half, so that'd be 5. Okay. So there we are then, and that is the shortest length it can be when it forms basically a perpendicular or a right angle triangle. But yeah, okay. Okay, let's have a look at part B then. It says, given that AC is instead, so we're going back to our sort of generic triangle. We're told now that AC is 12, so we actually can get rid of that, and now we know it's 12. Calculate the angle ACB, so that's this angle theta there. So this one then, well, we know two angles, well, we're dealing with two angles and two sides, right? So it's going to be the sine rule in this case. So again, the angle facing this theta is 10. So we can say then that sine theta over 10, using the sine rule, is then going to equal this other angle 30, and it's facing the length, the side 12, right? So it'll be over 12. So there we are then. So then to get for sine theta, we're then going to be doing 10 times sine 30 over 12. We'll put all that in a calculator. I get sine theta is 10 times sine 30 over 12 is 5 over 12. Okay. So then theta then, well, as we know, we need to consider there will be two solutions to this, two possible solutions. If we consider the first of all, one solution is always going to be the inverse sine. So theta could be inverse sine of 5 over 12, which is 24.62 blah 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 degrees, right? Okay, so we got that angle, but then again, of course, we need to consider another possible angle in this case, right? By using this the ambiguous case. So to work out the other angle, then, well, it helps us maybe consider the sine curve, because we know one solution is this, right? If we draw the sine curve between 0 and 180. So this solution is 24.7, that's probably going to be about there, say. So then if we read off the graph, the other solution will be about there, right? And so again, the gaps are the same between either end and the solution, although that's a bit off. There we are. Hopefully you can see that they are indeed the same gap. There we are. Right, so to get this other solution for theta here, well, it's going to be 180 take away this angle 24.62. Because again, if the gap is actually 24.7 either end, right? You know, that solution, that angle theta is the gap. So therefore 180 take away that gap will get me this other solution there. And so if I work that out then, 180 take away 24.62, I get 155.38 degrees. Okay, so I've got two solutions then. But again, I need to check this one, if this one makes sense. So to do that then, let's consider our angles. So we know in this triangle we had 30 and the angle theta, which is here 155.38. Let's add them and see what happens. So we have 155.38, add the angle 30. If I do that calculation, I get 185.38 degrees. Right, so that would mean then that again 185 degrees, so the angles in the triangle then, in this triangle, that cannot happen again, right? Because all three angles in the triangle must only add up to 180. I've gone above that. So therefore I only have one solution, which is indeed this 24.62. So I'm going to then say as angles in a triangle, sorry. Sum to 180. That means that theta cannot be this 155.38 degrees. So the only solution is that therefore theta is 24.62 to 2 decimal places, let's say. Okay, there we are then. Okay. So then part C says, given instead that AC is 7 centimeters, calculate the two possible values of angle ACB. Okay, so I've drawn the triangle then here. I recreated it. So now, again, the length is now 7. So again, we need to find the values of theta in this case. So again, we're going to use the sine rule like the last question. So firstly, we have sine theta here. And it's going to be facing that length 10, that side of 10. So we're going to have sine theta over 10. And it's going to equal, well, the other angle's 30. And it's facing the 7, the side with 7. So it's going to be sine 30 over 7. And so therefore then, sine theta is 10 lots of sine 30 times 7 over 7. And if I put all that in a calculator, I get 5 over 7. So then if I inverse sine it, I get the first value of theta to be this 45.584 ... degrees. But always with this, I want to consider the other value. So again, the ambiguous case of this sort of sine rule. So the other solution, again, if it helps, I can draw the sine graph to visualise what I need to do. So between 0 and 180. So the first solution is 45, it's roughly, so it's going to be about, say, there. 45.6. So then the other solution is going to be there, right? So then again, I'm going to utilise that the distance, the gaps are sort of equal between both ends, right? And the gap is indeed this 45.6, right? This solution here. So then again, the other solution then is going to be 180 take away that. So it's going to be 180 take away this 45.584. which I worked out. So then it's going to be 134.415 dot degrees. Okay, so I've got two values of theta. Right, and so obviously I should always check if this is a plausible solution. Now, probably spoiler alert, it's going to be correct because it's asking for two possible values. So they're both going to be correct. I could leave it there if I want to, if I'm a little bit careless, but I know I'm kind of right because the question asked for two values and I got two values. But to confirm to myself it's true, well, if I then check by adding this 134.42, add this other angle in the triangle 30, that will get me 164.42. So that's clearly less than 180, so that would be fine. And actually, therefore, then the other angle in the triangle would be 180, take away that, which would be 15.6, roughly, there. So that is a possible triangle I can have, right? So I can almost have two different triangles in that case, right? So I've got two possible values of the angle theta, which is angle ACB, there. And that it can happen because, as we saw, the angles do add up nicely. It's valid, right? So I've got two valid solutions then. If I restate it, I therefore have that theta is either 45.6 or 134.4 to say one decimal place. And there we are then. Cool. Let's have a look at another question then. Okay, it says two triangles ABC are such that AB is 4.5, BC is 6.8, and angle ACB is 30. Work out the value of the largest angle in each of the triangles. So again, I've got some stuff with lengths and stuff, so probably best to draw a little rough triangle to see, put all my information in to see clearly what to do. So if I have the point A, then the point B, say here, and then the point C here, and therefore I've got my triangle by connecting the points there. So firstly, AB is 4.5, so that's here, and BC is 6.8, and I've also given angle ACB is 30. Now again, C is the middle in the angle here, so it's at C, so it's 30 there. Okay, so it's asking to work out the value of the largest angle. Okay, so I need to work out the angles then essentially. So I need to find an angle. So I've got two angles because a missing angle and this angle 30, which I know. So I'm dealing with two angles and two sides because I've got these two sides as well. Well, then it's a sine rule, right? Because obviously the key idea of the sine rule is we're dealing with two angles, two sides, right? So, okay, so this sine 30, this 30 and is opposite to the 4.5, so we're going to have sine 30 over 4.5, and it's going to equal another pair of opposite angles and sides. But which angle? Well, we're given the side 6.8, so the angle we can work out from that. Well, what angle is it facing? Well, it's the angle at A, as you can see there. So that will then be this theta we're working out. So we can then say sine theta over that 6.8. So that's the angle we're going to work out with the sine rule. If we then work that out, well then to get sine theta, I'm going to times both sides by 6.8. Times by sine 30 over 4.5. And so then I get 34 over 45. So then if I do the inverse sine on my calculator, I get the value of theta here is 49.073 degrees. Okay. Well, of course, that won't be the only solution for theta. There'll be another one as well, because again of this ambiguous case, that's this produces two angles actually. So then I can visualize on the sine graph to help me see how to work out the other one. So between 0 and 180 again. So 49, that solution is going to be like there, right? So then the other one is going to be, if I go across like that, it'd be there, right? That'd be my other solution for theta. Again, how am I going to work that out? Well, again, I noticed the gaps at either end of at either side are the same. Again, there and there, and that gap is the first solution. So therefore, the next solution is 180 take away that solution, and that's always how I'm going to get the next solution. Okay, 180 take away that, remember, it will always be 180 take away that first solution, but the sine graph helps me to visualize that, but anyway, so if we work that out, then 180 take away that answer, I get 130.926 ... degrees. So I've got two possible solutions here. So let me then quickly check that is valid. Well, I can do it in my head really. I don't need to write it down. But 130, well, on my calculator even. But this 130.926, if I add that to the other angle I already know in the triangle, which is 30. If I add that to 30, I get 160.92, right? That's below 180, so actually that's a valid solution here. So I've got two solutions. So therefore theta is either 49.1 degrees or theta is 130.9 degrees to one decimal place. Okay, so those are my two possible angles in this case for theta there. Right, but what it's told me is not to work out that angle particularly. It's asking to work out the largest angle in each of the triangles. Okay, so now you probably think, there's two triangles? How does that make sense? It's because we've got two angles, so these will produce basically two different triangles. Very similar, but it's just the angles will change. So let's take this first solution, theta, 49.1. If I draw that triangle again, something like that, right? So this angle theta would be 49.1. And the other angle is 30 here at C. If I label it CAB. So then to work out the largest angle, well, let's consider the remaining angle at B, right? Well, that angle then, so this angle ABC then, because the angle's at B, that's how I label my angle. This remaining angle, like, they all have to add up to 180, right? So let's go back to that triangle property. So I need to take it 180 away from the two angles. So 180, take away this 49.1, take away this 30. And then if I do that, I get I get 100.9 degrees. Well, in this case, that is the largest angle, right? If I put that in, say, that is the largest angle. Out of 100.9, 49.1 and 30, that is by far the biggest one. So therefore then, here, the largest angle is angle ABC, which is 100.9 degrees to one decimal place. So that's one triangle, but then I need to consider the other solution for theta. So that would give me a second triangle, right? So again, if I redraw my triangle here, it's all the same. So this was 30. This was theta at A. Now it's going to be 130.9. That's the other solution there. So then again, in the well, actually, you should probably spot that this 130 is going to be the bigger angle. I don't really need to compute that, but I can do it if I want to just cover all my bases, be very thorough. Well, this angle ABC, at this case, the angle at B, is again 180 take away these two angles, which is 130.9 and 30. If I do 180 take away those two angles, I get 19.1 degrees. And so therefore then here, the largest angle in this triangle is angle at A, right? So it's going to be angle BAC, which is 130.9 degrees. Cool. So yeah, so I get two different triangles based on the two different solutions I get for theta. There. So yeah, so again, you must again, this question hopefully emphasises how important it is to consider the other solution for the angle I get, right, which again is called this so-called ambiguous case. Ambiguous meaning like which angle for sure. We have to take both angles. Anyway, we need to consider both angles when solving. Must always be doing that from now on with the sine rule. If we need to solve for an angle. So there we are. So let's have a look then at an exam question to finish off. And I will say this exam question is not as nice as it seems. It's the devil. It's not as it's just not as easy as it seems. There are a bit. There's ways this question trips you up, which we'll go over as we go through it. But this is basically then giving us some information. It's a bit of a wordy question. So as usual, I just want to extract the actual numbers from it. So firstly, AB is 12. Well, they're giving us the diagram quite kindly. So AB is 12 here. BC is equal to BD, which is 7 meters. But BC here is 7, and so is BD here. And then the angle BAC, which is the angle at A, is 27. Well, that's that. Okay. It says then define to one decimal place the angle ACB. So the C's in the middle here, so it's at the angle at C. So that one in triangle ACB. So I'm going to call that theta then. So that's what I need to solve. So if I draw the triangle here, say, to help me, I have ACB. This is 27. I know this length is 12. I know that's theta. I also know this is 7 up here. Well then, this is just a classic sine rule question I can use here. So, firstly, the angle theta is opposite or facing the 12. So we're going to have sine theta over 12. And then it's going to equal, well, the other angle is 27, and that's facing the side 7, the side BC. So then that's over equal to sine 27 over 7. So then to get sine theta on its own, I times both sides by 12. So 12 lots of sine 27 over 7. And that will get me then that sine theta, if I simplify that. Well, 12 times sine 27 over 7 is 0.778 dot dot dot. So therefore then, if I inverse sine that, I get the first solution to be 51.1 degrees, right? Say to one decimal place, but there we are. Okay, so at that point, I imagine most students would probably say that's the answer, right? Because the question basically suggests there's only one actual value for the angle, right? Because it's singular, right? The size of the angle. So I guess people will be tempted to say that. But this is where this question gets devious, because we need to actually consider the ambiguous case again, so the other angle. So the other angle again would be again, so if I draw my sine curve again between 0 and 180, so the first solution is 51.1, so that's going to be about like there, say. So the other solution is going to be like there, okay? So then to find the other solution here then, well again then it's going to be 180 take away that my angle 51.1. Again, because the gaps here at both ends are the same there. So anyway, if I do that on a calculator, I get 180 take away this 51.1. I get 128.5 degrees there. Right, okay. Well, actually, let's consider this can happen then. So let's look at adding the angles we have in the triangle. If we then said 128.92, add the other angle in the triangle, which is 27 here, right? That would get me 155.92 degrees essentially. Well, that's below 180, so it can be a possible solution then. That's perfectly valid. So we've got two possible solutions. So how come we only need one then? Why is the question asking me for only one? Well, this is where we need to look at the question and the diagram, because remember this angle theta is here. That's what we solved. Now we need to actually look at the angle, because the angle we can see is obtuse. So remember, you got an acute angle, so an acute angle is less than 90. So if this is 90, which is a right angle, then an acute angle is less than 90. So it's going to be, say, like there, right? So that's an acute angle, which is less than 90. And an obtuse angle is on the opposite. So if that's 90, then it's going to be like down there, right? And that is an obtuse angle, which is greater than 90. So we literally need to physically look at the angle in the diagram and see it's literally obtuse, right? There, because a right angle would be roughly like there, so that would be 90 roughly, the perpendicular to that line. So then there's a bit of angle left over, so it's obtuse. You can also alternatively, if it helps, consider the other angle here in the triangle, which is clearly acute, right? The right angle would be there, but clearly we only got this part of the angle. So it's acute, so we've got two acute angles, and because this one's 27, that means this angle here has to be obtuse, right? So we need to visually see the diagram to work out it's going to be an obtuse angle here, right? Obtuse angle, so it's going to be above 90 for theta. So that's literally what I have to do, so yeah, so then that means as theta is obtuse then, as we literally just need to look at the diagram and see literally the angle, right? So theta is obtuse, so that means we have to take the solution above 90, which is actually this one. So theta is then 128.9 degrees to 1 decimal place there. And there we are then. So actually it is the other solution in this case. A lot of people would probably fall for the trap for the first solution, but it's not, it's the other one. So that is why considering the other solution is very important. You must always, with the sine rule, consider the second solution, as this question proves here. Okay, part B then. So have a look at the other question, the other part. So it says the steel beams can only be bought in whole metre lengths. Find the minimum length of steel that can be bought to make the complete structure. So this is basically asking for the perimeter, so all the lengths of this whole triangle here. Basically all the lengths. Right. So what do we have? Well, we know this, AB here is 12. We know this length here is 7, BD. BC is 7 as well. So really the only length we need to work out is AD. How are we going to get to that? Well, we know this angle now for theta is it what we worked out. We're going to need to use that, right? They didn't ask us that. They didn't ask us to find the angle for no reason. So that's 128.9. I'll do it here actually. Squeeze it in there. So that's 128.9. I'll leave it there. Well, so how can I work out AD? well, I can work out this angle, can't I? Because again, I know the two angles of the triangle, so I know that angle as well. That'd be that angle here. So that'd be angle ABC, and that's going to be 180. Take away the other two angles, right? I might get something with that, right? Just the idea is what I'm doing at the moment is to work out what I can do, what I know, what I can do, right? And then I'll go from there. So 180 take away 128.9, take away the other angle, which is 27, which will get me 24.1 degrees, which is going to be there then. So that's 24.1 degrees. So we've got all three angles in this triangle ABC. Okay, well actually I can also work out this angle here as well. Because then this whole angle here is on a straight line, right? This 128 angle at C and the other angle would have to add up to 180. So then if I do 180 take away this angle 128, right, it was 128.9, right? That's going to get me 51.1. So this angle is 51 there, 51.1. Okay, well actually also this triangle BCD is isosceles because two of the side are the same, right? There's 7. So BD and BC are the same. So then that means this angle here is also 51 as well. So we've worked out a lot of angles here. Again, that's the key strategy of these sort of questions, is to work out and fill in any missing angles if it helps, if you're stuck. Well, actually, then if I draw the whole the whole triangle, right? Let's do it up here. If I draw the whole triangle ADB, oh, that's a bit rubbish. There, I know this angle's 27. I've worked out that this angle is 51.1. And I also know that this side is 7, BD. I also know this side is 12. Well, I want to work out AD, because remember, if I worked out AD, I know all the lengths, so I can work out the perimeter. So this AD then, I can use the sine rule, right? Or the cosine rule, actually, but I think the sine rule here. Because, not quite, because I need to work out this angle, right? Because this angle is facing the X. Well, I can work out that angle as well, because I know the other two angles in this triangle, so I can work out the third one by doing, so angle ABD is going to be 180 take away the other two, so 27 take away 51.1, it's going to get me 101.9 degrees. So there we are then, 101 there. So then I can use the sine rule then. So then I could say the length x then over the opposite angle to it, which is sine of 101.1, which we worked out, 0.9, is going to equal the, well, another pair of opposite angles and sides, right? Well, we can take this, right, this 7 and 27, angle 27. So 7 is the side over the sine of 27, which is the opposite angle. So then I can therefore say that x then is going to be sine. I'll do it down here actually. That have a lot of room. So therefore x then is going to be sine of 101.9 times the 7 over sine 27. And so if I do that on a calculator, I get that x is sine 101.9 times by 7 over sine 27. I get 15.087 dot dot dot, which is 15.09, right, to say 2 decimal places. So then I know what AD is as well. If I then get rid of these angles I have in this diagram, so I know that side. I know this side AD is 15.09. So now I have all 4 sides. So now I can work out the perimeter, because it's talking about adding steel beams to the edge of the structure, right? So the overall perimeter then, if I do it down here, first it's going to be this 15.09 that we worked out. Add the other sides, which is 12 and 7 and 7. Okay. Which is 41.087 meters, I believe. So there we are. Now, been very, very nearly there. Quite a nasty question, this, isn't it? Okay, but it's talking about the steel beams can only be bought in whole meter lengths. So, from the minimum length of steel needed to make the complete structure, so we need to round it up then, because it can only be whole numbers, that's what it's saying. So, we need a bit more than 41, right? So it needs to be 42 steel. Therefore, we need 42 steel beams required. And there's your answer. Okay. So yeah, that's not the nicest question there. Yeah, I mean, both parts of that were quite challenging. I mean, part A, having to realise the angles of obtuse, and you needed to pick the other angle, the other solution. And then part B, trying to find this AD length by considering all the angles we could work out, and then using the sine rule or something from there. But yeah, hopefully you kind of followed along with that. It's not the nicest question, but yeah. So that's the sine rule. So again, when you're using the sine rule from now, remember it is a step up from G to C. So you would always need to consider these when you're finding an angle from the sine rule. You need to be considering the second solution as well, by maybe using the sine graph and realising the other solution is going to be if this is the first solution and the other solution here is going to be 180, take away the other solution there. Okay, so you need to find 2 solutions with the sine rule with an angle, which we call the ambiguous case. But yeah, so that's the sine rule.